the first cause of landslide, the first factor that may cause landslide we have discussed is stability of slope. See, why we should take care of stability of slope, why we should take care whether the slope may cause failure or not. In case of low intensity of rainfall, this is first case, the slope may fail due to erosion. See, in case the intensity of rainfall is low, the top layer may get eroded off, and this reduces weight of overburden on the bottom layers, and actually this will favor the stability of slope. That is, the slope is stabilized in case of erosion if the intensity of rainfall is low. Suppose the intensity of rainfall is high and permeability of soil is also high. See, this is one of the causes of failure or landslides in Idukki district recently happening in Kerala, because when the British people came, large trees were uprooted, fell off, and this caused the permeability of the soil to be high. Now when the intensity of rainfall increased, see, the water is penetrating deep into the soil, and this forms deep into the soil. See, underneath the laterite rocks, laterite soil. See, this in Idukki district, laterite soil or laterite rock pieces are there. Beneath that we can see charnakite rock. That is, this rock supports the top. Now in between these two, this penetrated water mixed with the clay form an oily layer, and thus a separation will happen and large layers of soil will be eroded as landslides. So erosion can favor or cause a land, can favor the stability of a slope, but at the same time can be a cause of landslide. Now, score by rivers and streams. It's the same as erosion only. First case, erosion due to rainfall. Second case, erosion due to streams or rivers. See, one more thing is there. Sudden drawdown case. That is, if there is a sudden drop in level of water adjacent to the slope, this can cause a seepage force within the water present in between the particles made up of the slope. In between the particles of sand made up of the slope. Due to this seepage pressure, soil piping can occur. That is another topic. Seepage, due to seepage force in dams and all, failure of dams due to seepage can take place. Similar is the case due to sudden drawdown or drop in level of water adjacent to the slope. That is, for any landslide to occur, or for whatever the soil particle to come down, it has to overcome the shear strength of the soil particle. So if I am saying the mathematical representation of the seepage forcing, the shear strength of this shear strength of the slope, if we are considering, whatever that be, if I'm just saying about sand, that is, what is sigma is, see, we will come to that and all, just to make you understand about the seepage force. That is, if shear strength is given by sigma tan phi plus c and all, tau, or see gamma h, gamma dash h is sigma, and tan phi plus etc. And the seepage forces, gamma dash means if it is saturated soil mass, so we have to find gamma saturated, which is nothing but gamma minus that of water. Okay, and what is the seepage force? Seepage force is pressure due to pore water pressure, and it is nothing but gamma WH. So and this gamma, yes, gamma saturated, gamma minus 1, there gamma is that of soil, which is nothing but G gamma W. So this has to be balanced anyway. The seepage force, or the force gamma W delta H, that is due to some force. If there was water level like this and some water has come down, so there is a difference in pressure within the between, so the pressure will within the water present between the soil particles, so this water will have a tendency to come down. That is what. So that is what I meant, and we have formula and all for that. Next is thin rainfall, or during same is the case. Third one I have said, rainfall fills crack and introduces seepage forces in the thin weak soil layer. So same as what I have said just now. Then gravity and earthquake forces. Gravity due to the weight of the soil itself. So this weight of the soil, if it is more than, if weight of the soil has a strength, let it be gamma h and all. Now it has, the soil in itself has got some shear strength. So if this shear strength is overcame by the weight, then there can happen a landslide. So next, now coming to analysis of stability of slope. So I have said, for any slope to fail, this what happened during failure of slope, large masses come down. For these large masses to slide down, this shear, see, if I have a slope like this, and what is landslide? Large particles are coming down. That is, this coming down happens due to some weight and all. Let it be due to happens due to weight. So weight of soil. Now opposing this we have toe or shear strength. That is the force which acts parallel to the plane of failure. It is nothing but shear strength. This shear strength by weight of the underlying soil particles and cohesive force. this shear strength can be achieved. And Moore-Coulomb has obtained a failure criterion based on this. That is, shear strength we have if the shear stress on the soil exceeds this τ value, failure happens. That is Moore-Coulomb failure. If τ due to some external force, this shear stress is greater than τf, what happens? This implies failure of slope. And we have this τf given by sigma dash tan phi dash plus c dash, where c dash is effective cohesion, sigma dash is effective stress, that is sigma minus u. Whatever pore water present will not support any soil. It only causes decrease in shear strength. Okay, next, factor of safety. Based on this, we can say whenever we are considering a slope, we consider a factor of safety. That is, suppose we are making a road cut, we'll make sure that the slope won't cause any failure. Suppose we are making a road cut and we have a side slope, we have to make sure the side slope will not fail. For that, what we can do, make sure the height of cut is such that shear stress won't exceed its this whatever Moore-Coulomb criterion is followed. Just make sure that. So whatever we find and calculate, we just give a factor of safety, or we multiply that with, so as to make sure about its strength. So we can define factor of safety by two ways: ratio of shear strength to shear stress, ratio of shear strength to cohesion. Now one more thing is there, factor of safety based on sliding, based on overturning, it can be based on sliding. And sliding means what? The vertical force is weight, that is sigma v by sigma h. That is, this is factor of safety, so as to make sure the slope will not fail by sliding. Now overturning, it is nothing but sigma moment external by restoring, sigma moment restoring, moment due to external forces by restoring moment. So so as to make sure the slope will not fail by overturning. So we will see in detail in the following. Now many studies have taken place in this site, and that is how to analyze stability. So we have two types of soil, that is slope, finite slope and infinite slope. Now infinite slope means the slope remains constant or as such for an infinite extent. Just like if we have a mountain range, suppose if we have a mountain or a hill, suppose we have a mountain range, some total of hills are there, that is the slope continuously varies, so there we have finite slope. Okay, now here we will go see stability analysis of infinite slope on sand. On sand means it is cohesionless. So here I have shown in this figure, shown you a slope. There, how to analyze? We have to find shear stress, shear strength and all. Okay. So we have vertically downwards weight of the soil acting vertically downwards, and this is toe shear stress, and upwards we have reaction force. Now beta is angle of the slope we have considered. Angle of the slope we have considered. I'm sorry. Now how to analyze this? So that for that we have this weight as, suppose vertically downwards we have the pressure as gamma h. We in more mechanics of structures we have this normal stress sigma 1, sigma 2 and tau and all. I think you are remembering those things. So if we have a block of mass and sigma 1 is acting like this, then for any inclined plane we can find normal stress acting on that and shear stress acting on that. Similarly, here we have sigma 1 as gamma h vertically downwards. Now on the inclined plane with angle beta, we have normal stress sigma n as gamma h, normal stress sigma n acting on the inclined plane, gamma h sin square theta, and sigma t or shear stress, here it is represented as tau, so I am using tau as gamma h sigma 1 minus sigma 2 is 0. See, P1 cancel, just cancel. Gamma h sin theta cos theta. So here it is beta, angle of the inclined plane. I'm sorry for that. Sin beta. Now tau for this sigma n will be gamma h sin square beta tan phi is the, as per Morse Coulomb criterion, the maximum or the shear strength is the maximum, or the failure happen if it exceeds gamma h sin square beta tan phi, and C is 0 here. See, we have tau f as sigma dash tan phi dash. Sigma dash is sigma minus u. Suppose there is no pore water pressure. Considering the case there is no pore water pressure. So for maximum case, this sigma t tau f both should be same, considering the special case, that is gamma h sin square beta tan phi ultimate case equal to, what was the other, gamma h sin beta cos beta. That is, for the ultimate case we have tan phi equal to cot beta. And one more thing you have to think about is phi I have taken, or beta they have given is with respect to vertical. And one thing we have to notice is that we haven't noticed also, that is this phi, this angle phi is with respect to vertical. Now here this beta is with respect to horizontal, so we have to take 90 minus beta in our calculation, and we will be getting the limiting equilibrium as tan phi equal to tan beta, that is the ultimate condition. So what we have to require, this beta should be less than phi, that is tan beta should be less than tan phi for making sure that the shear stress acting on the slope is not exceeding its strength. Okay, that is what I meant to say. And now based on this we can get a factor of safety. Is given by tan divided by tan phi. So I think now you have got clear about how we analyze. Now so we have seen analysis of infinite slope in case of sand. Now consider the case of clay. So clay has cohesion as well. This cohesion will provide strength to the slope. So in this diagram, as you can see, we can have this Mohr-Coulomb's equation as sigma dash tan phi dash plus C dash, where C dash is the effective cohesion. So in the graph we can see the line representing this equation, this one. So its slope is phi dash only. Now in case of slope beta, that is, this line shows the shear stress acting on the slope, and the shear stress acting on the slope, and this is the shear strength of the soil, which is represented by this line. So the limit or the ultimate shear stress is given by this point A, where both are equal, like we have done in the case of sand. So what we have, sigma can be given by gamma h. Gamma h is the vertical stress acting on it. So the normal stress acting on the slope is, if this gamma h is sigma 1, it is sigma 1, we know it is sine square beta. So gamma h sine square beta. Now this sine square beta is with respect to horizontal, so we require angle with respect to vertical. So 90 minus beta it will become. So finally it will turn out to be cos square beta. Then you understood, beta is the angle in the figure, it has been given with respect to horizontal. We require that with respect to vertical. So it will come out to be gamma h cos square beta tan phi dash plus c dash. So this is to be equated to shear stress acting on the soil. So what is the shear stress due to weight? Gamma h sine beta cos beta. So we have discussed the ultimate condition of infinite slope in case it is made of clay. Okay, now we need to get the factor of safety with respect to that. So factor of safety, don't have confusion with while deriving factor of safety. Whatever ultimate stress it can handle. So we know ultimate stress a slope can handle is given by Moore-Coulomb equation. So we have found out it to be sigma n dash tan phi dash plus c. So it is gamma, here it is gamma h cos square beta tan phi dash plus c dash divided by whatever stress act on it, present case, that is ultimate divided by working. It is factor of safety. That is factor, we require factor of safety to be greater than 1, so that the working stress is always less than ultimate stress. Okay, so just remember that point, then you will not get confused. Divided by whatever stress act on it, it is given by gamma h cos beta sin beta. Okay, now see here we have a confusing equation. So for better representation, what I am doing is just giving this gamma h cos square beta as sigma m dash tan phi dash as phi m dash plus cm dash, where m represents mobility, that is the stress at which the slope become mobile. Just remember like that. So it is given by sigma m dash, factor of safety is given by sigma m dash tan phi m dash plus cm dash divided by the working stress on it, presently whatever stress is acting on it. Okay, now It is gamma H cos beta sin beta. Now suppose it is purely cohesive soil. That is, for purely cohesive soil, there is no friction. No friction means phi is 0. Phi is 0. So in such cases, we have this factor of safety reduced to Cm divided by gamma H. So and so. Now this gamma varies with respect to the seepage conditions of the soil. If it is completely saturated soil, then it becomes Cm dash by gamma saturated times height of the soil. Now there is another thing which you may note. This expression is given by stability number. There is another expression called stability number Ns, which is a dimensionless number given by C dash by gamma H. If factor of safety is to be included, just C dash by Fc gamma H. This is the stability number. Okay. Usually we have charts available with this stability number. We can just refer to stability number corresponding to any type of soil and proceed with the construction. So what I was saying was about gamma. Gamma can be gamma saturated if we are dealing with saturated soil. If fully submerged, then it have to be gamma submerged, which is given by gamma sat minus gamma W. Okay. Next, till now we have discussed infinite slopes. Next topic is stability analysis of finite slope. Finite slope means the slope is of a finite extent. We have a limited length of slope which we have to analyze. Now within which we have two categories for this stability analysis. Two categories and two assumptions as well. Okay. So I will say, first of all, we can analyze the slope as a whole. Take the whole slope, consider its weight acting at the center of gravity downwards, and so and so. Then analyze. Another thing is, cut the slope to slices. As whole, as slices. These are the two ways you can analyze. Cut the slope into slices. I will show you. If we have a slope like this, then if we have to analyze this much portion, we will cut this into slices, and for each slice we will take its weight, its cohesion or whatever, pore water pressure, everything we will consider for each slice and analyze. Now I said about two assumptions, that is, the slope failure can be assumed to be linear or circular, means rotational. The slope failure can be assumed to. So different geologists have used different types of analysis, and we have in textbooks each analysis is completely explained there. That is, if considering the slope as a whole and failure along a line along its length, considering it into slices, and so on. This one. We will be seeing some of them. Now this one by Kuhlmann, where he analyzed the slope as a whole and he assumed the slope failure to occur along this line AC. Okay, and he analyzed the slope. Now we have initially this beta as the angle of slope, and see, after the slope failure, the slope angle has become theta, and then he analyzed using this force triangle, where we have W, weight of the slope overburden, as which is acting vertically downwards, and R is the reactive force upwards. So you will see Kuhlmann's method of analysis. Okay, he assumed the failure to occur along the toe of the slope. And what he has done, he considered the weight above the, beta was the initial slope of the initial slanting angle of the slope, and after failure has occurred, it has taken angle theta. It is the safe angle. So he considered that portion in between beta and theta. He considered that portion and formed a force triangle, which is shown in this figure. So the forces acting are weight of the soil mass acting vertically downwards. So W gives the weight of the soil mass acting vertically downwards, and R is the reaction force, and C gives the cohesive force. Now from this triangle, he just found out the factor of stability. See, C by, we can just apply sine law and all. That is for C by sine theta minus phi dash is equal to W by sine of, so theta minus phi plus 90 minus theta, 90 minus phi dash, so 180 minus 90 minus phi dash will give 90 plus phi dash. So sine of 90 plus phi dash is nothing but cos of phi dash. This is how he analyzed. By differentiating the equation obtained by solving this force triangle for obtaining a critical angle of slope, he obtained the angle as half beta plus phi, not theta. That theta C dash was obtained as half of beta plus phi. Further, he obtained at critical condition C by gamma h is equal to 1 minus cos beta minus phi divided by 4 sin beta cos phi. From this we can find out the critical height of slope. Okay, so that was what he found. Now stability of slope is stability factors with respect to cohesion can be obtained as factor of safety with respect to cohesion as per Coulomb. He has considered the landslide to occur along a plane. Now if we consider rotational failure, then the solid soil mass can slide along a circle, and this circle can pass through the toe or below the toe or above the toe of the slopes. That means if this is the slope we are considering, the failure can take place along the toe or above the toe or below the toe. So these three cases are there. Now the method usually used to analyze rotational failure is friction circle. Now in this method we will consider a trial circular failure surface as shown in this figure, along which it will slide, and a friction circle such that tangent to the circle at any point intersects the trial circular failure surface at an angle phi dash. Then we will be analyzing it for stability. So what all forces we have to consider are weight acting vertically downwards, boundary neutral force, which means actually pore water pressure only, and we find it using flow net diagram. That is, this flow net diagram will give you the potential difference along which water will flow, that is hydraulic gradient, and then the along which water flow, thereby pore water pressure. Now we are least concerned about that. I mean with respect to geotech, it is actually coming under hydraulic section. We have to consider that force also. Then intergranular pressure, that also acts along the boundary. So these are the forces we have to consider. Since it is rotational failure, see, I am introducing a new factor of safety, that with respect to overturning. So if we are considering cohesive force, so you will get to know how we analyze using this. The mobility cohesion is Cm dash, that is due to which it failed. And the other one, C, effective cohesion, is C dash, So it acts along the length of the circle. Now the effective cohesion we have to consider. We have assumed the failure to occur along a critical circular surface of arc length LA. Okay, now the moment due to this will be about the center of the friction circle if you are considering times r. So this is the moment. Okay. Now cohesion LC dash. So we have to consider a chord LC along which the force acts. C dash LC into. Now the moment. We are assuming it to act at a distance LA. This much distance we are assuming to be LA, which is called moment gap. Now the ratio of this will give you the factor of safety with respect to cohesion. So now with respect to strength, if we are considering, it will be tan phi dash divided by tan phi m dash with respect to strength. So this is the way we analyze. Now if we are considering the method of slices, similar to the other case, we have to consider the forces of weight, cohesion, and pore water pressure. Now this weight itself has two components, which is one along tangential and the other along the normal direction. So these are the forces we consider in method of slices and take factor of safety. Okay, how we take factor of safety? Just take the sum of all forces along normal. And take the other one too along tangential. We are considering the moment of the forces and taking the ratio, that is moment that support the slope, provide stability to the or the strength, moment that goes moment that resists overturning effect divided by moment that goes overturning as the factor of safety with respect to overturning. So how we do that is shown in this figure. See, this shows the resisting forces on the base of the slice, that is cohesion and the normal forces. Okay, now what forces cause overturning? The component of the weight along tangent, that is this sigma, we have to divide the slope mass which fail, we consider to fail. Okay, here also we assume an arc of failure, and then do all the analysis. Okay, after dividing into slices, we have to consider each slice, find cohesion, weight, whatever, the normal component, tangential component, pore water pressure, etc. After that, we have to take the sum C dash L plus tan phi dash into sigma n minus u divided by sigma t. So this is the factor of safety.